Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. I am on some kind of pseudo vacation, not in my usual place. I thought I was going to have an exotic backdrop, but that doesn't work technically. So I've got an even more boring backdrop. I've been wandering around this island all day, so I'm probably still looking a bit overheated. But all right, we've got a bunch of questions that were saved up from previous times. Oh, here's a fun one from Derek. The question is, why are there no trees in the ocean? Well, let's see. Let's start off with what the difference between plants and things that live in the ocean are likely to be. So one key feature of plants is they have photosynthesis, that is, they use energy from the sun to succeed in making energy for themselves, and they do that by having they do that mostly with their leaves, and they're making use of they're making use of the light of the sun to do that. If you are underwater, then except in a very narrow zone close to the surface of the water, the sunlight doesn't get through to you enough that you could really use photosynthesis as a source of energy. So the idea of having leaves with chloroplasts and things in them to do photosynthesis is, and using chlorophyll, which is what makes plant leaves green, as a way to get energy isn't going to cut it. It's interesting. Chlorophyll is a very clever molecule. It's a protein, but it has these kind of clever quantum effects that it uses to take photons of light from the sun and succeed in making energy. And it's only in fairly recent years there's been even a somewhat decent understanding of how that process works. And I think it's fair to say that plants fundamentally use quantum mechanics in some sense in their mechanism for making energy through chlorophyll and so on. But in any case, that mechanism in the first, few feet, tens of feet maybe, of the ocean, there's still enough sunlight that you can have like green algae that still have chlorophyll in them as a way to make energy. But by the time you're deeper than that, you're dealing with red algae and so on. You're dealing with things that don't get their energy by having light from the sun. And I think so that's a sort of a fundamental reason for sort of things with leaves and so on. And by the way, also an important feature of the way trees work is they have this, the woody piece, xylem or whatever, which has all these little channels in it that allow it to pull water from its roots up to use the mechanism of evaporation from leaves and so on as a way to produce pressure that pulls water up into the leaves of the plant and so on, into the upper parts of the plant. Again, not a mechanism that one would expect to want to use in the case in the ocean. Now, another thing about trees, I guess, is that if you're a tree, one of the important things is to stick your head out high enough, so to speak, that you can get your leaves to actually see the sunlight. And if you're a tree in a forest and there are lots of other trees there, there's sort of a struggle for who can get their leaves out, as the uppermost thing so that they get lots of sunlight and so they're not shaded by lots of other trees. And so I think that's sort of a motivation for a tree to just grow bigger, taller all the time. And that motivation in most of the ocean isn't going to be very useful because grow as you might, you're not realistically going to grow, half a mile up through the ocean to get to the point where you can get energy from the sun, so to speak. So I think that will be another sort of the big idea of trees, of have this very solid trunk that lets you sort of support leaves very high up. I don't think is so likely to be a thing in the ocean. I think it also probably doesn't help. Here's another question I don't really know the answer to. A tree obviously is subject to wind and the wind will make the tree kind of, if there's a strong wind, it will push the tree in some direction, and so on. And if and there's a question of sort of how strong the tree needs to be to not be destroyed by the wind. I'm right now on an island called Nantucket that has very strong winds a lot of the time, and you notice that a lot of the trees are very are not tall at all, and they're very, you can tell that they're kind of, they exist in the form they exist because they have to withstand high winds for much of the year. So the question is, in the ocean, where there are ocean currents, I don't know what the relative forces exerted on a kind of ocean tree by ocean currents will be relative to the force of wind exerted on an ordinary, tree on land. But I think that might be a factor, that it's very hard to have a rigid object that would be successfully kind of sort of grow up in the ocean, because I don't know, but I think it may be that the forces associated with ocean currents will be enough to kind of destroy any sort of material that you try to set up in that way. Now, I suppose I can't be completely correct about that, because something like an oil rig that has some, as a drilling platform or something that has great big steel supports, it is obviously subject to those same ocean currents, but on the other hand, it's be made of steel, which is a stronger material, although not much, than things like wood of trees. But so I'm not sure that I'm not sure how successfully I'm answering this, but I think the sort of the motivation for having a tree-like thing with woody stuff and leaves that are green and so on, it doesn't really work the same way in the ocean. And instead, what you end up with is lots of kind of algae that big pieces of seaweed that stretch a long way, but they're very floppy, and they just sort of they float in the ocean currents and so on, I think, rather than being this kind of rigid structure that you see in trees on land. An interesting question I don't know the answer to is, one of the characteristic features of trees is these phyllotaxis spirals that you get. When they produce successive shoots, they will tend to always be at this 137.5 degree angle relative to each other, because that's the angle that, well, it's produced by a rather simple process of kind of diffusion of plant hormones in the growing plant, but it also has the effect that sort of successive branches least shade all the other branches that come before them. And you see the same kind of phyllotaxis spiral on pine cones, on the leaf scars of palm trees, on the structure of raspberries, on all kinds of succulent plants, all kinds of places. You'll see the same phyllotaxis spiral. And as I think about it, I don't remember immediately aquatic examples of that. I don't know cases where in kind of aquatic algae type life, sort of the phyllotaxis spiral have been discovered. It existed in you can find fossil plants from the Cambrian period, for example, that already show evidence of these kinds of things. But I don't know whether it's been sort of discovered by algae or whether algae kind of need it. Maybe they don't, because they don't have the same sort of issue of avoid shade type thing. So anyway, a rough approximation to an answer to that question. Let's see. Aaron is referring to a previous stream where I said that one of the books I had for potential beach reading, I have to admit I haven't been to a beach actually yet this week, but was Immanuel Kant's Critique of Pure Reason. And yes, I got through the first few pages, but I haven't got any further yet. My main takeaway so far, Kant wrote a bunch about kind of how to think about our view of the world, so to speak, and what is kind of, how our sort of sense of the world relates to what actually exists in the world and things like this. And I have to say that, having thought a lot, particularly recently in connection with our physics project, about questions like that, I just feel much more empowered to read what Kant had to say than I ever felt in the past. Because in the past, I was like reading this stuff and I just don't, it's hard to understand. and I just didn't have sort of a framework to put it into. Let's see. Well, there's some questions here about okay, there's a question from Zagan. The difference, what is the difference in relation between computing and modeling? You know, okay, let's see what I can do with that. So what is computing? Computing tends to be, you have certain rules defined by a program, and computing is about taking different inputs that you can provide, applying those rules and getting outputs. So for example, you might have a program that computes some mathematical kind of thing. You might have a program that generates some image or something from certain input. So the typical picture of what computing is, the sort of the typical idealization of computing is there's a program that defines a set of rules for going from an input to an output. And often in sort of the simplest models of computing, it's really all about input to output. And the journey of what happens in between is not so important. Now, realistically, when we run computers today and we've got our interactive, you know, our operating system and running all kinds of interactive applications, the interactivity of those applications is in some sense part of the journey. The things the applications progressively do are sort of part of the journey. And maybe we are providing additional input by clicking the mouse or doing this or that thing, but it's a little bit different than the traditional input, rules, output type model of computing. Okay, so, and what do we typically do? We typically say, well, we want to write a program that does something useful to us, that takes our input and produces something that we care about as output. Okay, what's modeling? Modeling is all about taking something that otherwise exists in the world and finding some way to idealize that so that we can, for example, with a computer, reproduce the essence of what we see in that system in the real world. So usually those systems in the real world, they tend to be sort of dynamic kinds of things where there's a process that's going on. And the question is, can we successfully reproduce the essential features of that process? And I keep on saying essential features because as soon as you're saying, well, I want to make a model for the growth of a snowflake or something, or I want to make a model for the growth of a tree, when you make that model, you don't expect that you're going to reproduce exactly what every molecule in the snowflake or the tree does. Rather, you want to say, well, I want to get the basic idea of what happens in the snowflake or the tree. But one person's basic idea might be very different from somebody else's basic idea. One person might really, really care about the precise temperature gradients inside the snowflake. Another person might just say, well, I want to know roughly what shape it is. Is it very tree-like or is it very hexagonal or what is it? One person might care about the basic arrangement of branches on a tree. Another might care about what the overall shape of the canopy of the tree is. And so different models for a single phenomenon in the world, there may be many different models for that phenomenon, depending on what it is that you think you care about. Now, there's a question, how do you make those models? How do you figure out the idealization of what the system does so that you can reproduce the thing you care about the system? So, for example, you might say, I don't know, you've got a pendulum swinging backwards and forwards, or you've got a planet going around in orbit around a star. How do you make a model for that captures whatever it is you care about it? Like, where's the pendulum going to be at a certain time? Where's the planet going to be at a certain time? A big tradition of modeling that developed in the 1600s is this idea of using mathematical equations to make models. So writing down an equation that says there is a function of time that determines where the planet will be at a certain time. I think, and I've just actually been working on this in sort of the frontiers of my basic science efforts. I think one can actually identify, well, now 4 sort of periods of broad periods of sort of the modeling as done in science. And the first period one might call kind of the structural paradigm for modeling. That was a thing that originated in antiquity when people had the very good idea that all these different things in the world might be made of a fairly small number of common elements. Sometimes they thought those elements were, fire and water and air and so on. Now we think of those elements as being atoms and molecules and so on. But this idea that even at a larger scale than just atoms and molecules and things, that somehow you might be able to describe the things a thing does by talking about what its elements do, and that there might be a modest number of elements that operate with certain characteristics. And I think the typical thing in antiquity, and for the ancient Greeks and people like that, is how is the thing built up out of atoms, out of this, out of that? What is its structure? It's sort of a structural paradigm to thinking about modeling things. It's not very dynamic. It's not about how does this thing kind of sing and dance and change and apply rules. It's about what is the structure that gets built up. And that was seen in the, in ancient Greek times when people were talking about, epicycles, for where the planets might move on these kind of crystal spheres that have a certain structure. And that was kind of that paradigm. The big thing in the 1600s was the idea of let's introduce a new piece of raw material for making models of things, which is mathematical equations. Let's write down an equation, usually they were differential equations using calculus, that would describe this question of what happens as a function of time. Well, another paradigm for modeling, which is one that I was much involved in introducing in the 1980s, is this kind of computational paradigm for modeling, where instead of saying we've got an equation and it describes as a function of time what's happening, rather what we have here is something that that term as a function of time I should remember to mention in this piece that I'm writing, because that's a good perhaps way to describe some things. But in any case, in the case of the sort of computational paradigm, it's instead the system operates according to certain rules that you can embody in a program, and you can say the system starts this way, and then you apply these rules, and this and this and this thing happens in the system. So in a sense, modeling in the computational paradigm is very much like running programs and computing. That's kind of what the idea of the computational paradigm is. But there is a bit of a difference, because in a sense, typically in computing, it's like, I want to get some answer. I don't care how the program works inside. I just want to get this answer. In modeling, you're much more concerned with, I want to kind of see at least certain aspects of the steps, because that's the story of what the system that I'm doing, that I'm looking at does. And so there's more of a kind of look inside the thing to see a little bit more what the mechanism is. Now, you don't want to look too far, because in the end, a model is a kind of abstract idealization of a system. If you're doing models with differential equations, you don't imagine that the planet has a differential equation solving piece of software inside it. Instead, it's just the planet behaves as if it is following what the differential equation says. So I think that in a sense, the motivation of modeling is a little different than the motivation of computing, because the motivation of modeling tends to be, we see these things in the world, now let's get a program that reproduces what those things in the world do. Whereas computing tends to be, I have a thing, an idea that I want to execute. Now let me write a program that executes that idea. It's a little different. Now, something that goes sort of in between those two is machine learning, where you'll typically have something where you say, here's a set of things, here's a set of examples of how things work in the world. I want to train my program. I want to create a program-like thing that has been trained based on these examples to do the things that I want, or to follow those examples in some way. So I think the sort of interplay here is between, on the one side, computing is about sort of answering or solving a problem you want to solve, just working out from input to output something, whereas modeling is more about reproducing the important aspects of every stage in the progress of some particular system. And as I say, in the previous paradigms for modeling, that was very different from the sort of computational paradigm for modeling. In previous paradigms for modeling, you would just say, this thing is described by this mathematical function. not there are a progression of steps, like in a program, that specify how the system should behave. Now, one thing to realize about models is when you write a program for computing something, you usually kind of have in mind the objective of that computation. When you model something, the only objective you have is make it do something like what the system does. But the system itself may not have the same kind of global objective, or usually won't have the same kind of, can't be identified as having the same kind of global objective. You know, when you have a flow of some fluid or something, it just does what it does. It doesn't have a global objective in the same way that a program that you write for some particular purpose of computing something will tend to have a sort of global purpose. Let's see. Gosh, lots of questions here. So question, why are thorium nuclear fission reactors not more popular? You know, it's strange. I live in a strange world because I was literally talking to somebody about something which leads to a discussion of thorium reactors just this morning. I was talking to a person who's a long-time expert on particle accelerators. And one of the applications for particle accelerators is thorium reactors. Okay, let me try and explain a little bit about how these things work. So your average nuclear power station, the way it works is it has a bunch of uranium or plutonium in it, and those elements have the property that they are radioactive, and in particular, they, with some probability, a nucleus of uranium will spontaneously break in two and kind of spray pieces of itself all over the place. It does that sufficiently slowly that it's actually been, there's uranium that is sort of been waiting to do that for billions of years since the Earth was formed. So when you mine uranium out of the ground, one of its isotopes, uranium-235, that means it has some 235 neutrons plus protons in the nucleus. It has 92 protons, and the remainder, let me not embarrass myself by doing the arithmetic wrong, the remainder of its 235 particles in its nucleus are neutrons. So anyway, the uranium that existed when the Earth was formed is still, with some small probability, self-destructing. So the average time it takes for a uranium-235 nucleus to self-destruct is like a couple of billion years. So still left over from when the Earth was formed 4.6 billion years ago, there's still a bunch of uranium-235 that exists. So you mine uranium, and you can put a bunch of uranium-235, for example, into a nuclear reactor, and some of those atoms of uranium-235, their nuclei will self-destruct. Every time a nucleus self-destructs, it spews out fragments, which include a bunch of neutrons, and those neutrons then go hit other uranium nuclei. And when a neutron hits a uranium nucleus, the uranium nucleus will self-destruct. It will spontaneously self-destruct with very slow rate. But if you hit it with a neutron, it will just go kaboom and immediately destruct. So what happens in a nuclear reactor is that you have a chain reaction. Those neutrons cause other uranium nuclei to break apart. Those things that break apart produce even more neutrons, and so then they make even more uranium nuclei fall apart, and so on. When you make a nuclear, what's happening is that's all happening sort of explosively. It starts off with the chain reaction starts off, and it kind of grows exponentially. 2 neutrons turn to 4 neutrons, turn to 8 neutrons, and so on, as they make other nuclei fall apart. In a nuclear reactor, you have control rods that basically, and you have a moderator that kind of keeps these neutrons from sort of going and destroying other nuclei, and you can kind of control the rate at which these neutrons are propagated through the core of the reactor, and you can kind of keep the reactor away from going critical, so to speak, and ending up having something where it can generate too much heat and melt down, in the sense that it, when all these nuclear reactions are taking place and nuclei are falling apart, that's generating lots of energy that ends up as heat. And if there's too much of it, it will mean that this lovely nuclear reactor that you had, that's got a bunch of metal structure in it, will all melt. And that's what happened, for example, at Fukushima, and it's what happens when there are sort of typical accidents in nuclear reactors, is it melts down in the sense that everything gets too hot, and the structure and the fuel rods and all these, and the moderator and all this kind of thing that kept the reactor under control is all goes away. Okay, so enter thorium. Thorium is an element which doesn't, which has the property that it will undergo fission, its nuclei will fall apart, but it needs a little bit of a kick to do that. And you can give it a kick by using a particle accelerator to just take a bunch of protons, accelerate them with magnets, make them go very fast, ram them into the thorium nuclei, and that will cause the thorium nuclei to self-destruct. And that, as those ones self-destruct, they start a little reaction where more of them self-destruct and more, but the reaction doesn't go on in the same way that it does in a uranium reactor. At least that's my understanding of how it works. And so it's kind of a way to have something where there's no way to make a bomb out of it, because you just can't, it doesn't spontaneously, there's no spontaneous process of having the thing generate, undergo fission and generate more neutrons and so on. But as soon as you kick it, right sort of where you kicked it, something will happen and it will generate energy from the breaking apart of these nuclei. So in order to make this work, you need a particle beam, a beam of high energy protons, let's say, to make this work. But the energy you need to produce that beam of high energy protons is presumably much smaller than the energy associated with what comes out from the nuclear processes in the thorium. At least that's my understanding. Now, why I think people have worked on trying to make sort of reality out of this, I don't know precisely the status of that. I will say I learned another thing about sort of uses of particle beams in sort of things related to nuclear reactors, which is one of the problems with nuclear reactors, is they produce nuclear waste. Nuclear waste is random isotopes, random elements that, and here's how it usually works. When, for example, uranium undergoes fission, it will fall apart into smaller nuclei. And they'll be just sort of random smaller nuclei. So might be a nucleus which has a very short lifetime. So the uranium atom nucleus will fall apart. It will produce, some weird isotope of copper or something, and that isotope of copper will decay in a microsecond to some other isotope of, I don't know, zinc or something, and that will decay to something else, and so on and so on and so on. And so long as that process basically happens, so long as all you get are isotopes that decay quickly, until you get to a stable isotope, you're good. You don't leave over any kind of radioactive waste. The bad case is if this chain of reactions leads you to something like, I don't know, strontium-90 or cobalt, what is it called? There's an isotope of cobalt which has this property as well. And the problem with these isotopes is they aren't stable, they're radioactive, but they have a very long half-life of like 100 years, let's say, or something like that. So if you end up with, making randomly, as you kind of spray out different fragments of uranium nuclei and things, if one of those fragments is a strontium-90 nucleus, then you can end up with something which has a lifetime of hundreds of years. And so you can end up with something which is not stable, it's not radioactive, it's still, and it's not so radioactive that it will decay in a microsecond or something, but it's still radioactive. So it can cause trouble and it can get into groundwater and it can make, all sorts of terrible things radioactive and so on. And so the difficulty is these sort of intermediate time scale radioactive elements, radioactive isotopes. It's kind of a strange thing that the same process of radioactivity can have vastly different lifetimes. can lead to, so for example, alpha emission, the emission of a helium-4 nucleus, 2 protons, 2 neutrons, which is a pretty common way that radioactive nuclei fall apart, as they emit an alpha particle, which is that 2 protons, 2 neutrons thing. And they do that, and that causes them to turn into another isotope, which might again emit an alpha particle, or it might emit an electron, or it might undergo spontaneous fission, or it might have some other decay process that makes it radioactive. But one of the things that's sort of mysterious is that alpha emission, there are examples of alpha emission where the half-life, the expected time before the alpha particle is emitted, is microseconds or billions of years. And it's very rare that there are things that span that many sort of different orders of magnitude for a phenomenon. And actually, the reason it happens that way is because it's sort of a mathematical fact. There's an exponential function that appears in the probability for alpha emission. And the way that works is, essentially what's happening is, the way you can think about it, there's a quantum mechanical phenomenon called tunneling. And essentially what happens is, if you have something where, okay, so you have, let's say you're rolling a ball downhill, and the ball is at the top of the hill, it has lots of potential energy, and as it rolls down the hill, that potential energy is turned into kinetic energy. The ball rolls faster and faster under gravity. It just does what it does. Okay, now let's imagine there's a big bump in the hill. There's a big, it's running down, and then it runs into this bump, and that bump is pretty high, and it can't, the kinetic energy that it got running down to that bump is not enough to get it over the bump. And so in ordinary classical physics, it's like it doesn't get over the bump. The thing just stops, and it can't get any further. But in quantum mechanics, there's a phenomenon called tunneling that you can see as kind of a result of various uncertainty principle arguments and things. But basically what happened, well, the general idea of quantum mechanics is it is not the case that sort of definite things happen in systems. Instead, the systems kind of sniff out all possible paths for everything that could happen. And what we get to work out is just probabilities for different things to have happened in the system. And so what happens in this case of when you have the equivalent of the ball rolling downhill and this big bump, is that in quantum mechanics, there will be some kind of possibility that the ball will do this weird thing that doesn't really conserve energy in a sense, and it manages to jump over the bump and come out and go down the other side. But the way quantum mechanics works, there's a small probability of that happening. But that probability gets exponentially smaller the bigger the energy gap is. And so what happens in alpha decay is the same kind of thing. There's essentially a barrier to these alpha particles sort of getting out of the nucleus to this piece of the nucleus. That's what an alpha particle is, a piece of nucleus sort of breaking away from the rest of the nucleus, getting outside. There's kind of an energy barrier that prevents that happening. And the height of that energy barrier determines what the probability of that happening is. At every moment, it's like there's an alpha particle rattling around, it wants to get out. And the question is it going to make it out or not? And the question whether it makes it out or not, there's a certain probability it makes it out at every second or something. And that probability is determined by the height of this barrier. And it is an exponential dependence on the height of the barrier. Now, an interesting question is there an easy way to derive that exponential? And for example, in our new models of physics, is there an easy way to understand why tunneling involves an exponential degradation as a function of energy? And I think I did think about this at some point. And I think there may be an argument for that. I can't immediately reproduce it. But basically, the fact that this alpha decay phenomenon has this vastly different, from microseconds to billions of years, possibility for the average time before the alpha particle comes out, that the lifetime for decay of the nucleus is a consequence of this exponential factor from tunneling. But anyway, that's some. But so I was going to say, when you have a nuclear reactor and it has nuclear fission going on, that means nuclei are sort of being sprayed apart into all these different pieces. And the bad case is one of those pieces happens to be a century-ish lifetime, or even a few years, even a decade or something, lifetime nucleus, because then it can it won't decay to nothing. It'll be hanging out. It'll be radioactive. Radioactivity causes all kinds of trouble for us humans. It's kind of bad news. I should say, why does radioactivity cause trouble for us humans? Well, what happens is when there's radioactivity, you have you're getting these particles, like an alpha particle, for example, emitted, and these particles are going very fast. So when these particles go through a tissue, through you, for example, they will disrupt the atoms that are in you, because when they zip past, they're like applying there's some electrical force that they're applying to the atoms in you, and that will tear those atoms apart. And in particular, it does very bad things to DNA, for example, and it will tend to destroy the genetic material in DNA. It will tend to produce sort of changes in genetic material that can lead to cancer, things like that. In general, with enough radiation, you just kill cells. And that's indeed what you do in radiation therapy for cancer, for example. That's indeed what you're trying to do. You're trying to say, this little spot of cells is a tumor and it's growing without bound and it's bad, let's kill it off. And so you concentrate this radiation on that particular spot to kill off those particular cells. And radiation kills cells by a variety of methods, but one of them is destroying sort of the genetic information in DNA and so on. So, and that's what, and usually, if you get exposed to radiation, all sorts of terrible things happen, but there's sort of a whole cascade of things that happen that depend a little bit on the lifetime of cells. Like, there'll be things with blood cells that last, where they last 3 months or something. And then as the next generation is supposed to be produced, it doesn't succeed in getting produced because there's radiation damage to the genetic material and so on. So that's sort of how that comes about. But in any case, the question is, if you've got this nuclear waste, what are you going to do with it? And if there's all this radioactive stuff that might be radioactive for thousands of years even, what do you do with it? And so people have tried to figure out, where do you put nuclear waste? And so, for example, there's a lot of controversy about, do you put it in do you put it in a deep mine where you bury it underground? And do you encase it in glass so that it's sort of more kept away from the elements? If you put it deeper, if you bury it underground, there's a problem that it can kind of seep out and get into groundwater, and groundwater can go other places, and that's bad. And it's, if you could send it, you can kind of, you can try and put it somewhere. You could maybe send it into space. You could, if you had enough effort, you could throw it into the sun or something, and that would definitely be a good way to dispose of it. I actually just recently found a funny essay that I wrote when I was like 11 years old about problems like that, which concluded that the right answer was to make spacecraft that would do sort of garbage disposal by throwing things into the sun. But it's a rather impractical kind of solution. It was then, and it still is, a rather impractical solution. In any case, one of the exotic possibilities for getting rid of nuclear waste is, what if you just zap the nuclear waste with a particle beam? If you do that, it's kind of like what's happening in the thorium reactor. You're kind of zapping it, and you're causing these nuclei that right now are sort of radioactive nuclei and things. You're breaking up those nuclei, and you're causing them in the next kind of random roll of the dice of what happens when you break up the nucleus. The chances are you're not going to get one of these troublesome isotopes anymore. And I think it's the case that by the time you get down to the lighter elements, there are no troublesome isotopes anymore. So they're either things disappear quickly, or they are basically stable and don't cause trouble. I don't think that can quite be correct, because tritium, the isotope of hydrogen that has a proton and 2 neutrons in its nucleus, it has a half-life of about maybe 10 years or something. I know that was sort of a funny phenomenon, that from the nuclear tests that were done in the atmosphere in the 1950s, there is a bunch of tritium in seawater that kind of spread itself throughout the oceans of the Earth. And when I was a kid, at least, and you asked how much tritium is there in a typical sample of hydrogen, there was one number. The number is different today, because the tritium that existed from the bomb tests that had been done in the 50s was still around when I was first learning about chemistry and things in the 1960s. And so it still contributed to the fraction of hydrogen that is tritium and is pretty much all decayed by now. And so it no longer makes a contribution there. All right, let's see. There's a comment from Icy about, since with DNA being a double helix, shouldn't it work with something like error correcting codes? Yeah, well, DNA does have proofreading enzymes that try to check that it's sort of correct. So here's basically what happens is DNA is transcribed to RNA. Then what happens is every 3 base pairs of the DNA or the RNA, which is, in other words, every 3 of those things, the A, C, G, T, A, G, A, T, C, G, those are the 2 pairings. Every one of those base pairs, what is a base pair? A base pair is a cluster of, a few tens of atoms on this backbone of the DNA. So the DNA might, a chromosome might have 100 million different base pairs. Each one is either an A, a G, a C, or a T. And when to say it's one of those letters is to say it has a particular cluster of atoms that is strung along this backbone. And so, our genetic material, our genetic code is encoded in that sequence of A's and G's and C's and T's. Okay, when the genetic code is used to produce proteins, the way it works is that every 3 of these base pairs, like A, G, C or something, might be a triple base pairs, every one of those makes a so-called codon, and every codon codes for an amino acid. And there are about 20 amino acids that at least we use. And those amino acids are the building blocks of proteins. Proteins are sequences of amino acids strung together. And each time there's a sequence of 3 base pairs, it makes one of these codons, which codes for one of the amino acids. Okay, so important point. If you have 4 possible base pairs, that means that the number of possible triples of base pairs is 4 cubed, which is 64. And that means there are 64 possible codons that you can get, but there are only 20 amino acids. So in the early days of DNA, people thought, oh, biology must have discovered error-correcting codes just like we humans have, and there must be some elaborate way of doing this coding that very carefully, optimally error corrects. It doesn't seem to work quite that way, but nevertheless, it is the case that there are legal and illegal codons, and there are proofreading enzymes that can go down a DNA strand and kind of fix the ones that are obviously wrong. But so in that sense, that can be done. And when DNA replicates, it is common for there to be some amount of error in the replication when the 2 strands of DNA peel apart and then another strand is filled in alongside the strand that sort of zipped apart. There's a question of, does the strand that fills in exactly and correctly match, C with G, A with T, and so on, or are there errors? And there's a small rate of errors. And that small rate of errors is actually, in the end, not bad, because that's what leads to the random mutations that drive biological evolution. But the actual rate of errors is higher than you would want from biological evolution. And so these proofreading mechanisms come in and try and fix the obvious errors, so to speak. So that reduces the rate of errors to something much smaller. It's a little different for viruses and things like that. They have different mechanisms for doing that. Well, let's see. Okay, there's a comment that I think is about nuclear waste here. If you dilute the nuclear waste back to the same concentration as the ore and put it back in the mine, would there be a problem? Yes, there is a problem, because what you got out of a mine is uranium. What you're putting back is one of the fission products of uranium, which may be something much nastier than uranium. So it's not good enough to just say, put it back to the same place where you were, because you don't have the same place where you were. I mean, it's worth realizing that in different, and when you do chemistry, you say, I've got this element, it's hydrogen, it's carbon, it's gold, whatever else. And whatever atoms of gold or carbon or whatever you have, that's the number of atoms. The number of atoms you put in is the number of atoms you get out. You can't transmute an atom of lead into an atom of gold, for example. That was the goal of the alchemists throughout the Middle Ages and beyond. Sort of the thing that people really wanted to do with chemistry was to find a way to turn base metals like lead into gold, which was sparkly and shiny and valuable. And so they wanted to, just by chemistry, turn lead into gold. But it wasn't possible, because what turns out to be the case is that whether you're lead or gold is determined by the structure of the atomic nucleus, and chemistry is just about changing the electrons and the way the electrons kind of wrap around the nucleus, and how those electrons cause different atoms to be close to each other and to be bound in with chemical bonds and so on. And it's not about changing the structure of the nucleus. So these ideas, so in order to change the structure of the nucleus, you need a nuclear process. And that means, like, if you zap lead with a particle beam, for example, you might be able to turn a little bit of it into gold. But you have to zap the nucleus with a particle beam to change the structure of the nucleus. And so that's what, so there's no purely chemical process which can change radioactive waste into something that's not going to be radioactive, because you need to change the atomic nuclei, and that's not what chemistry does. You might be able to use chemistry to separate out one kind of chemical element for another. One of the things that chemistry does is it can separate one element. I don't know, it could separate lithium from beryllium or something, but it cannot separate one isotope of lithium from one isotope of beryllium. So, for example, when you have water, there are different isotopes. Ordinary water just has hydrogen with a single proton in its nucleus, but there's heavy water which has hydrogen, which has hydrogen in which there's a proton and a neutron. Deuterium, it's called, is as the hydrogen. So, for example, D2O is just like water, and as far as chemistry is concerned, as far as the electron properties, it is basically just like water. But as far as the nuclear properties are concerned, heavy water is very different from ordinary water. Heavy water is actually very useful in nuclear reactors because it absorbs neutrons a lot, whereas ordinary water doesn't absorb them nearly as much. But as far as chemistry is concerned, it's not quite true for heavy water. Heavy water has slightly different characteristics for chemistry, but most of the time, different isotopes, by the time you have heavier elements, different isotopes don't have different chemical properties. They only have different nuclear properties. So no chemical process can separate isotopes. So, for example, one of the big things that's necessary for making nuclear reactors and so on is the separation of uranium-238 from uranium-235. And there's no chemical process alone that does that. And so what you have to do is you have to use, you can use some physical processes, because you can use the fact that you can use gas diffusion, because a uranium-235 atom has slightly less mass than a uranium-238 atom. And so when it's diffusing, when the atoms are bouncing around and moving a certain distance in a gas, the uranium-235 atoms will move slightly further than the uranium-238 atoms. So you can use that as a method for separating these things. But there's no chemical process where you do a chemical reaction that will tell apart these isotopes. Let's see. Well, I should probably wrap up soon here, but well. I'm being told that the internet connection here is not perfectly stable. Well, I hope it's been okay. Ethan is asking, what is my altcoin portfolio? Boy, okay, that's I'm actually losing track of what cryptocurrencies I have stakes in. I know some of the bigger ones, but they're kind of random and historically determined. maybe for another time, we'll talk about different cryptocurrencies and how different cryptocurrencies work and kind of the different objectives of different cryptocurrencies. Maybe let me take one more. Oh boy, a lot of interesting questions here. Ori asks, can the world become more valuable even though there isn't more stuff being brought in from outer space? It's an interesting question. So it relates to very foundational questions about economics. I mean, that is, how much is the world worth right now in dollars? If you were going to sort of pay for everything in the world, I don't know what it is, maybe $100 trillion, whatever it is. What is it the case that over time that the value in dollars of the world will go up? And if so, how could that be? And in countries, you try and measure some kind of value. I mean, it's a little complicated measuring the value of something because, in a sense, let's say you have an object or a company, something like this. You say, how much is it worth? Well, what that really is asking is, if somebody was going to buy it from you, how much would they pay you for it? Okay, what does it even mean to buy it from you? It means that if they say, oh, we'll buy this company for $100 million, they're saying that they think that $100 million that they could be using to buy candy bars or whatever else, that $100 million is as usefully put into owning that company as it is used for buying candy bars, for example. And so that so in other words, that there's an exchange that the thing that was worth X number of dollars could be exchanged for all other things which are similarly worth X number of dollars. In other words, the concept that something is worth something is this idea that there's many different things you could exchange it with. You have this thing, and there are lots of other things that you could want instead, and you're assigning a value to the thing based on what the sort of exchange with all these other possible things would be. So I think when it comes to asking about the sort of the overall, well, when you ask about countries, for example, you talk about GDP, gross domestic product, which is more of a revenue computation than it is a net worth computation. It's more how much money is churning through the country than it is how much is this country worth. You can get some estimate of how much is a country worth by asking for things like, what's the value of the real estate in the country? What's the value of all the stocks of companies in that country? All those kinds of things. But I think one of the sort of surprises and interesting things is that there definitely is the impression that the value of the world is going up over time. And why could that possibly happen? I think the reason that happens is I think ideas, processes, discoveries make the value of the world go up. And I think the reason for that is that in some first approximation, that the more we learn about how to do stuff, the more efficiently we can do things. And somehow that translates into the concept that the things we have. So for instance, okay, let's take the raw material for a smartphone. The question is a smartphone worth more than the sum of its parts? And what about a smartphone is worth more than the random pieces of aluminum and silicon and tantalum and who knows what else that goes into a smartphone? In what sense is the value of the smartphone as finished goods greater than the value of its component parts? And I think that it's that process of putting the thing together into this finished object that is sort of adding value, and you can progressively add more and more value to the world as you have more and more ideas about sort of how to put together a taller and taller tower of sort of sophistication. I mean, first you have the smartphones, Then you have the networks that can be created by people using smartphones. Then you have this, then you have that. You're building this kind of tower of ideas or abstraction. And I think the reason that the value, the sort of perceived value of the world can go up is that part of the value has to do with the sort of this frontier of new ideas and new things being constructed and figuring out how to do more stuff. Now, what does that really mean? I mean, I suppose at some level that means, we humans live a certain number of years, at least at present, and there's how much can we do in that amount of time? How much can we achieve? And if we are kind of doing everything from scratch, growing our own food, tilling the soil and so on ourselves, there's much less that we can achieve than if we're making use of some giant tower of technology that makes use of all these inventions and ideas and this and that and the other to create kind of a sort of a kind of higher tower of efficiency. And I think that the maybe way to think about it is, in a human lifespan, for example, how much can be achieved in some sense of being achieved, and the fact that that is so much greater for the fact that there's all of this sort of this kind of taller platform that we've built through technology. And I think that's sort of the reason why it's not just a question of the raw material. In fact, I would argue that when it comes to information technology and so on, that there's sort of an infinite amount of value that can be generated there, even with the exact same raw material that we already have. So you don't need to drag, the asteroid made of gold to the Earth to have additional value, so to speak. You just have to have this tower of ideas that, in a sense, make what the computer does able to achieve more for a person, so to speak. So I think that's by sort of interpretation of why that it's the progressive development of ideas, the progressive development of technology that leads to increasing overall value for the world, where value is defined somehow as achievement per lifetime or something for people. I don't know whether that's but it's an interesting question. When you look at sort of the closed system of the world, how do you end up with growing economic value through the course of time, given that it's a closed system? And it's not like people are just saying, well, it's going to grow in value because I can sell that particular ore for more money than I could sell it for before because, well, it has this better use somewhere else and so on. Once you have a closed system, there are none of those stories that can be told. But I think that the thing that is sort of the constant of this is, the consumption is right now by humans, and there's sort of limitations like human lifespans that determine kind of that give you a scale for what things are worth. Now, an interesting question is, at a time when there are bots that are sort of transacting many of the things in the world, at a time when maybe there are humans somewhere in the loop, but a lot of the actual transactions are happening between AIs, how does one then see kind of the exchange of value? And can it be the case that once there are, AIs representing a large part of the economy, will you still get this notion of increasing value? My guess is the answer is yes, because it's the same idea. Technology never ends. There is always a way to sort of add, to discover more in technology, think of the next thing you could do. The only thing that defines kind of the endpoints of technology is what do you want to do? Because we can invent all kinds of wonderful technology to do all kinds of things, and people would look at it and say, we don't care. It's not something we care about doing. And what tends to happen is the sort of co-evolution of what technology makes possible with what it is that people think they want to do. And that kind of spiral sort of upwards as you imagine, technology allows you to do more things, so you imagine more that you can do, then technology enables you to do that more efficiently, then you keep going and keep going and keep going. There are no doubt many different directions in which that could go, but that's kind of the idea. And I think that spiraling process is what leads to an increase of total value, so to speak, at an economic level. Although I have to say that some details of sort of exactly how that argument works, I'm not completely clear on, and I've been thinking a bit about sort of the foundations of economics, and that's a good exercise actually to think about in terms of understanding that. All right, I should wrap up here for now, but thanks for joining me, and look forward to another one of these sessions, I think same time next week. So thanks for joining, and bye for now.